Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. This reaction involves the acid-catalyzed Nazaro type or diene-1-phenol type electrocyclic cationic rearrangement of a cross-conjugated triene, A2-methylenated 1,3-diene system bearing R-substituted vinyl groups. The starting material is a divinylmethylene compound, effectively a cross-conjugated system with the central exocyclic methylene and 2 R-terminated vinyl groups. Under H+, this undergoes acid-catalyzed cyclization. Step 1. Identify the starting material. The molecule has a central sp2 carbon is equal to CH2 with 2CH is equal to CHR arms. This is analogous to a divinyl carbinol precursor or a cross-conjugated triene that can cyclase under acid. Step 2. Mechanism of cyclization. Protonation at the terminal position or at the exocyclic methylene generates a stabilized allylic pentadienyl cation. The 4-pi or 6-pi electrocyclic ring closure, conrotatory or disrotatory, leads to a 5-membered ring. The driving force is formation of a cyclopentyl cation or cyclopentadienyl system. Step 3. Identify the product ring. The cyclization of the pentadienyl system forms a cyclopentyl ring. After ring closure and rearrangement, the most stable product retains a single endocyclic double bond conjugated with the carbonyl, an alpha-beta unsaturated ketone is equal to cyclopentan. The R groups end up at C4 and C5, the saturated positions flanking the ring junction, and the double bond is between C2, C3. Conjugated with C1 carbonyl. This matches option B4, 5, desubstituted cyclopent 2N1-1. Step 4. Why not the others? A. Places the double bond at C3, C4, not conjugated with the carbonyl, giving a less stable non-conjugated enone, thermodynamically disfavored. C. Is a fully conjugated diene-1, cyclopentadienyl, which would require loss of more hydrogen and is too oxidized for a simple proton-catalyzed rearrangement. D. Is an alcohol, cyclopentenyl, not a ketone. Under H+, the equilibrium favors the ketone tautomer, not the enone. Step 5. Conclusion. The acid-catalyzed rearrangement gives the thermodynamically stable conjugated cyclopentane with R groups at C4 and C5 corresponding to option B. Therefore, the correct answer is B. Therefore, the correct answer is option B.